We are going to start talking about Ampere's law now. Okay, so I'm going to divide our study of Ampere's law into these 4 basic categories. Applications of Ampere's law. So the 4 main things we're going to study are going to be a long, straight wire, a solenoid, a toroid, and number 4, infinite uniform surface current flowing over XY plane. Okay, let's start with number 1. A long, straight wire. When we have a long, straight wire, I can find the B field here or a B field here. These are going to be called external points, and this is going to be called internal points. Let's suppose the radius for the external point, I'm going to call it A. And the radius for the internal points, let's say I'm going to call this B. Actually, I think I'm going to move this sort of in the middle so you guys can see them simultaneously. I'm going to do internal points here and external points there. So do you remember
Ampere's law?
Integration B dot dl equals mu naught I enclosed. Okay, so let's do external points first. Just like when we were doing Gauss's law, we used to draw what was called the Gauss's surface. In this case, we are going to draw what is called the Amperian loop. Okay, so what will the Amperian loop look like at the external point of radius A? What is the easiest way you can think of? A circle? Right? A circle that goes around, that covers the point that you want. So how will I write B dot dl in this case? Is B a constant? Yes. Over R d phi? From 0 to 2 pi for a circle? What is R in this case? I defined it as a A. Is A a constant? Can it be taken out? Integration of d phi from 0 to 2 pi is 2 pi. Or B equals mu naught I enclosed 2 pi A. Okay, now what happens to the interior points? If I'm looking at my internal points, if this is my cross section, like looking down at my wire, and I want to find the point at this, I want to find the B field here, what will my Amperian loop look like? Will it not look like this? Okay, just like we were doing for Gauss's law, may I write the left-hand side of the Gauss's law represented the Gaussian surface, correct? So in this side, the left-hand side will represent the Amperian loop. So on my left-hand side, what will my integration be? B integration B d phi from 0 to 2 pi. Is that true if this is B? And this is R? What about the right-hand side? What's the I enclosed in my Amperian loop only? Is it only this part? Agreed? What percentage of that is as compared to the whole? May I write that as I pi b squared divided by pi r squared? Does that make sense? So the I enclosed in my Amperian loop is only the area that is enclosing the loop proportional to the total area that's outside. Is that true? Follow ahead? Yes? So then may I write this as B, oops. Oh, I should probably make this dark. Do we all understand how this went from here to here, right? Okay, just confirming. Or B will just be mu naught over 2 pi I B over R squared. Now look at these two expressions. How do I graph this? If this is my radius R, this is my B. This is inside, and this is outside. How will I draw this? What will this graph look like on the inside? is the magnetic field proportional to R? As you increase your Amperian loop, will your B field increase? And the answer is yes. Until it reaches the surface. And then it varies as 1 over A. Here it varies as B, right? As the B field increases inside. And outside, it decays. So here you can write B is proportional to R, and outside B is proportional to 1 over R. Everybody happy with this explanation? Questions, concerns? Makes sense, right?